Good morning, Dr. Anil Kumar Singh ji. Yeah, Dr. Yatiraj Khare, good morning.
Good morning, sir. Good morning.
Yeah. So, can you switch on your video?
Yeah.
If it is possible, please switch it on because, so this is first time I'm seeing your face. Good morning, sir. Good morning. That's good. You are always active. Good morning, Dr. Raghavendra. Good morning, Dr. Dhananjay Singh ji.
Good morning, sir ji.
Good morning. So today that weekend effect is visible. It's almost 10-12, but we are only 21 now. So at 10:15 we'll start. So still few of you are not able to receive that login ID.
हाँ मैम चलना मैडम को बता देते हैं पेन वेन रखना है पेन वेन कुछ रख लिया
So I think it's already time. So let us start today's schedule. So we are 24 now, and maybe in between other people they will join. Let me remove this. Yes. Good morning, Mahesh. Yeah. So once again, a very warm good morning to one and all. Before starting today's session, so on the behalf of all of you and IRI, so let me wish you all a very happy Women's Day. So today is Women's Day, and then it is very important day for all of us. Good morning, Naik sir. So today's schedule is that good morning. So today we have three sessions, and today will Prakash, Dr. Prakash, can you please mute yourself? So today we have three sessions, one talk and two practicals. And today, I think all three sessions we are going to talk about protein, especially storage protein, and then some of the tools through which you can characterize the quality or the integrity of these proteins. And then our one of colleague, Dr. Vinutha, she will showcase some of the technology which has been developed here at IRI. So today it will be a protein come technology which we have developed here. So morning session, I'm going to share basic information about one of the most important tool, which I'm sure most of you have used one or the other way in your research work. I'm sorry for those who are at KBK or those who are from extension, because maybe it will be a little bit away from the topic which they know, but then you have always the scope to extract the information, because this will help you or this will fetch you knowledge. So today I'm going to talk about one of the very important tool of gel-based proteomics, that is SDS space. And I'm sure all of you might be knowing this SDS space. So what I'll do is I'll give you some of the basic informations that how you are going to use this SDS space to characterize the protein. For those who are from KBK and extension, let me tell you that many a times we used to talk about the quality of the seeds, and storage protein is one of the parameter which decides the quality of the protein. So question comes many a times we used to say that this is the quantity of protein which is present in the seed, or this is the quantity of storage protein which is present in the seed, but then many a times that quality is missing, and there are many tools through which you can analyze the quality of the protein. So one I'm going to talk now, and another Dr. Vinutha, she will be talking in maybe third session. So SDS space, as I told, it stands for sodium dodecyl sulfate polyacrylamide gel electrophoresis. So name is little bit big one, but then the short notation is SDS space. The purpose is that through SDS space, you can characterize the presence of different type of proteins in your sample. And it's not only the presence, but it will also tell you the integrity or the quality of the protein which is present in your sample. And if I'm using the term sample here, it means seeds. So because we are talking about pearl millet seed, which has a range of maybe 10 to 14% of the protein, which is on par with the cereals, especially wheat. So now when you have such quantity of storage protein, the question comes quantification you can do, but how to analyze the integrity or the quality or the presence of different type of proteins in your sample? So the answer is that you can go for SDS phase, which is a gel-based method very commonly used by the biochemist and molecular biologist. So I have made few slides to introduce you about the SDS phase, and then we have one video clipping. So one of my student, Mr. Kankan Pandit, so he has nicely explained all the steps in the form of video. So that will show you. So let us start with basic of SDS phase. So whether my slides are visible, any one of you can answer.
Yes, sir, visible.
Yes, sir.
Thank you. Thank you. So, so here we go. SDS Space, as I told, is one of the very common and basic tool which basically we are using. But then before going for the SDS Space, one should know the basic principle of electroforces. And I'm sure all of you might be knowing that this electroforces basically has been coined from the term electro and phoresis. So electro is your current, and then phoresis is separation. It means you are going to separate any biological entity with the help of the current on some basic material or maybe some base material. So that is the electrophoresis. Now, so who is the person who discovered this? So Arne Willem Corin Tiselius. So he is the gentleman who first demonstrated, discovered, and built an electrophoresis unit, which is also known as Tiselius unit. So he is a Swedish biochemist who was also awarded Nobel Prize for this particular discovery of electrophoresis. And here in picture you can see the instrument which is visible is such a big type of electrophoresis. Nowadays in your lab, if you see, we have a very small electrophoresis unit with us. So he is credited with the discovery of electrophoresis, and the instrument which he discovered is called as Tiselius unit. So now classification. So basically this electrophoresis has been classified based on the molecule which you are going to separate. So I think commonly what molecule we are going to separate is either DNA, RNA or protein. So if you are going to use the DNA or RNA, so we have different set of or the classification of electrophoresis, like when you are going to use the agarose as a gel, so you have a agarose gel electrophoresis. We have a sequencing gel electrophoresis where you are going to make a vertical SDS space. Then you have a pulse field gel electrophoresis. You have a capillary gel electrophoresis where you are going to use a thin capillary, and then you are going to pass the electric current so that your molecule will be separated. Similarly, in case of protein, we have different classifications of electrophoresis which we are using for the separation of the protein. Like when you are going to separate the protein for based on the molecular weight, so you have the SDS space, which will give you a very beautiful fingerprinting of proteins, or you can go for the protein profiling. Similarly, we have a native phase where you are going to analyze the activity of the enzymes or the proteins which are present in your sample, and this activity you are going to analyze on the gel. This is also called as electrophoretic mobility profiling of the protein. We have different classifications of this native phase, like we have a blue native phase, we have a blue native dyes, we have clear native phase, we have a QPNC phase. So these are different classifications of native phase based on the activity which you are going to analyze on the gel and the purpose for which you are going to use. Here dyes stands for differential gel electrophoresis. So if you have a control sample or if you have a treated sample, so in one go, in one gel, you can easily analyze those proteins. Similarly, clear native phase, this is very popularly used for metalloproteins or the membrane linked proteins. Similarly, QPNC phase for industries, so there people they are using this for high throughput characterization of protein. Similarly, we have another classification which is called as gradient phase, gradient polyacrylamide gel electrophoresis, where you are going to make a gradient of the gel, maybe from 4 to 14% or maybe from 8 to 18%. So like this, we are going to make a gradient, and then you are going to separate your protein based on their molecular weight. Similarly, we have a isoelectric focusing based characterization, which is also called as IEF. So here you are going to use IPZ strips, and then based on the isoelectric point of the protein, you are going to separate your protein, and further, if you wish, you can stain it, or otherwise you can use it for the two-dimensional electrophoresis. Similarly, we have a very a popular tool used in proteomics, which is a gel-based, that is two-dimensional electrophoresis. And in my talk also, I have explained this. So here you are going to separate the protein based on two different dimensions. One is your first dimension where you are going to use isoelectric focusing, and then you have the second dimension where you are going to use the SDS phase. Similarly, we have other cellulose acetate electrophoresis or continuous flow electrophoresis, which is very popularly used in industry. So this is a framework of different type of tool, electrophoretic tool, which we are using, which we are used for characterizing DNA, RNA or the protein. So today we are going to discuss one of the tool which is very popularly used for protein profiling, that is SDS phase. So this SDS space has many uses. The first question which comes in front of us is where to use this tool. So if your objective is to go for protein profiling, suppose if you have seeds of diverse accessions of pearl millet, and if you want to compare the storage protein which is present in these seeds, so you can go for the protein profiling. So what you have to do is you are going to extract the protein and you are going to run it on the gel, SDS space gel, and easily you can make out the appearance of the protein band and the variations in the appearance of these protein bands, which are basically storage protein. Similarly, if you want to find out the molecular weight of the protein, so SDS space is the best tool where easily you can run it on the gel, and then you can compare it with the markers which you have run, and then easily it will tell you the molecular weight of the protein. Similarly, you can use it to estimate the size of the protein. Even in case of peptide mapping, this is one of the most popular tool for peptide mapping. If you want to compare the polypeptide compositions also based on structure, so nowadays this tool is very popular. Even you can analyze the purity of the protein which you are going to use, even the integrity of the protein, the quality of the protein which is present in your seed, easily you can make out by running it on the gel, and then you can compare the appearance of the band. Similarly, this SDS space is the basic tool in case of Western blotting, where you are going to analyze the accumulation pattern of the protein. So n number of things, post translational modifications, even in 2D. So n number of things are there where you can use this particular tool for the characterization of the protein which you have extracted. So the basic principle of SDS space is that you have a protein with both positive and negative charge. Intrinsic charges, which is because of the amino acid which is present in your protein. And then when you break it down using some reducing agent, and then when it is labeled with a anionic detergent, that is sodium dodecyl sulfate, so it will unify the charge, and then your linearized protein is moving onto the gel based on the molecular weight of that particular protein. So this is the basic principle through which we are going to separate the protein which is present in your sample. So that is separation based on molecular weight. So now this SDS, we should know what basically this is. So this SDS is basically a detergent. So it disrupts the tertiary structure of the protein and bring the folded protein down to the linear molecule. And further, we are going to unify the charge of the protein using this particular anionic detergent. And once the charge is unified, then easily you can separate it out based on the molecular weight. So these are some of the basic information about the SDS, which we are going to use in case of SDS space gel. So now this is important, instrument and accessories. So when you talk about the instrument, basically which are used for this SDS space, so we have three different type of instrument which we are using in SDS space. One is your mini unit, another is midi unit, and then you have a large unit. If you see the cost wise, so mini unit that will cost you around 20,000 rupees, a midi that will cost you around more than 60,000 rupees, and then large unit, so almost 2 lakhs rupees. Regarding running time, so mini unit within 2.5 or 3 hours you can complete your run. Midi unit, it will take you around 4 to 5 hours, and large unit, so overnight you have to run in order to resolve the protein which you have extracted. And these are some of the accessories which basically we are using in case of SDS phase. Like you need to have a glass plate, a comb, a gel caster, a running tray, upper tank, lower tank, wire. So a lot of things you required, but then when you purchase this, all these things will come with your unit. So now coming on to polyacrylamide gel. So here you can see the cross-linking structure. So this polyacrylamide gel are basically made up of your acrylamide and bisacrylamide. So this is the polymerization of acrylamide monomers with the bisacrylamide. Easily you can make out in the structure. And then we are using timid and APS for the polymerization, or for initiating the free radical reactions for the polymerization of this. And bottom you can see the electron microscopy of this particular polyacrylamide gel. So here you can see small cubes or small holes present all over the surface. So this is basically the structure of the polyacrylamide gel which we are using for the separation of the proteins. So now coming on to the protocol for SDS space. So whatever I'm going to tell you, so this is in general, and the video which we have shoot, that is for the pearl millet grain. So in general, for any SDS space, so there is 4 or 5 prominent accessories steps. So first step is that you have to extract a high quality protein, and if your sample has some phenolic component or some other anti-nutritional factors, so that you have to remove it, or some admixture or some metallic ion that you have to remove before using that sample for the SDS phase, because all these things inert will disturb or will hinder the movement of the protein, and then there is every possibility that you will not get a very a good resolution and separation of the protein. So the first step is protein extraction, which is very important, and then based on the sample you have to decide which protein you are going to separate and how you are going to extract and purify that protein before being used for the SDS phase. Then another point is gel casting. This is very important. Many a times we miss this, and it will be half casted gel, and then we'll use it for the run, and the outcome is that you will not get the separation of the protein. Rather, there will be a lot of voids, and then your sample will not able to run. So gel casting is very important. You have to follow all the steps very with a precaution, and then once it is casted, you have to give appropriate time. Once it is casted, then only you have to take it out for the run or for the separation of the protein. Third is SDS phase run. So many a times what we used to do is, in order to complete your run within a stipulated time, we used to give very high volt or current, and the outcome is that your plate will crack, maybe because of the generation of heat inside that. Or many a times when you are giving a very high current, so that will have an effect on the running of the protein, and then you'll get a smiley face on the gel. So all these things happens on the gel if you are not following the proper protocol. So SDS phase run is also dicey, and you have to follow the exact protocols for the run. Then last is staining of the gel. We have different types of method used for staining. So earlier people, they were doing a Comase brilliant blue based staining. Then silver staining ruled the world, and then now we have a fluorophore based staining, where different type of phosphorus dye we are going to label, and then easily you can capture a beautiful efference of this particular radiation from your protein, and easily you can capture that. So staining of gel, different methods are available based on the requirement. You can use any of the method, but then as you go ahead with the silver staining or maybe fluorophore based, so cost will also increase. So till date, the cheapest one is the CBB based, Commercial Brilliant Blue based staining. And last is interpretation of results. So once you have stained your gel, so you should know how to interpret that, and then you'll get a very good resolution and very good separation of the protein, and then easily you can make interpretation. So I have included few slides for that. So coming on to the protein extraction, so here you can see the basic, as I told, whatever I'm going to present on the slide, this is a basic framework which anybody at any place can use and extract the protein. So here you can see that, so these if you don't have any specified mention that you have to extract your protein in a particular buffer, so you can use 100 millimolar TriCl with a pH 7.3. So this is a robust buffer which you can use for any sample. So using liquid nitrogen, you can crush, you can make extract in your extraction buffer, and then you can centrifuge, and you can get the supernatant out of that. Here we have shown it in the form of image. And suppose if you want to extract and purify your protein, so different kits are available. Like you can use total protein extraction kit, you can use focus proteome kit, you can use 2D extract kit. So different kits are available which will not only extract, which will not allow you to only extract, but it will purify your protein also. And then once you extract, purify, then directly whatever supernatant you are going to use, that you can directly use it for the SDS phase. So protein extraction, as I told, is very important. Based on the sample, you have to decide whether you have to go for the further purification or direct in one go extraction, whatever supernatant you got, that you can use for the SDS phase. So that you have to decide. But then this is a common framework where easily you can extract in 100 millimolar TriCl pH 7.3, and then you can use it for your SDS phase purpose. Next important thing is protein quantification. So you have to correctly estimate the protein, because when you are going for protein profiling, so there you have to load equal quantity of protein in all the wells. So different methods are available for the protein quantification. If you go for the basic method, so Lori or the Bradford method is one of the method of choice in almost all the labs. But then we have an improved kit also for the quantification of protein, like non-interfering protein protein assay kit. This is very popular kit. Or we have a protein quantitation kit by Amar Sham. So like this, a lot of kits are available from different companies, which can be used directly for the quantification of the protein. If you go by the instrument base, so we have three most popular instrument which popularly people they are using for the quantification of the protein. Like you can use a qubit fluorometer. This is a proprietary of in vitrogen. So directly it will tell you the quantitation of the protein. Or you can use a nano drop where you are going to use 1 drop of protein, and then easily it will tell you the quantity of protein which is present in this. Or the latest one is bioanalyzer, where you can use a chip and then you can put your sample. It will tell you the quality as well as the uh, quantity of the protein. So bioanalyzer has S over other two, that here you are going to analyze the quantity as well as the quality of the protein. So now coming on to the gel preparation. So here you can see, so different steps I have mentioned. So first step is that you are going to make a gel. You have to just mix in the proportion which has been written, that is acrylamide and bisacrylamide in a specific ratio. And once your mixture is ready, so one step which is very popular, just 1 minute. Sorry, there was one urgent call. Yeah, so I was telling that, so here we have a few steps which I mentioned here. First is that you are going to take this acrylamide and bisacrylamide in a specific proportion. One step which is very important, that is degassing. So you have to remove all the oxygen molecules which is present in your solution. So we have a vacuum pump, so you can use vacuum pump to degas your sample. And this is very important step also, because if oxygen molecule will be there, so this will not allow the perfect polymerization of your gel. So you have to degas it. Once the degas sample is with you, so you can pour from one side, as here it has been shown. So from one side, slowly you can pour your solution. The only precaution which you have to take is that there should not be any bubbling over there. If bubble forms, so that will hinder the polymerization of your gel. So once you are going to pour from the one side, then so as I told, this SDS phase, it is also called as a two gel system, because here you are going to use a two different gel. One is your resolving gel, which has a specific pH of 8.8, and then another is stacking gel, that is pH 6.8. So the purpose is that here you are going to stack your protein, and then once protein is stacked, then only you are going to resolve it in the resolving gel. So once you have poured the resolving gel of pH 8.8, then you have to allow it for almost more than half an hour to get polymerized. So once it is polymerized, then you can put the comb, and then you can pour the stacking gel, which has a pH of 6.8. Then again you have to leave it for 15 to 20 minutes, and then both these gel will be casted. So here one precaution which you have to take is, once you have poured the resolving gel, then the upper surface of the resolving gel, so this should be uniform. If it is not uniform, so it will not allow the stacked protein to enter uniformly inside the resolving gel. So for uniformity, either you can put some alcohol, so butanol you can add, or even water will work. Just pour some water, so that will unify the upper layer. And once the gel is casted, then again you can wash it, and then you can go for the stacking gel. So like this, you have to go for polymerization, and as I told, you have to take precaution that there should not be a formation of bubble in your gel. So if bubble is formed, so that will go on increasing with the current, and then it will hamper the resolution of the protein. So coming on to the next slide, that is the pH. So even this SDS phase is also called as a 3 pH system, because here you are going to use 3 different pH. So running buffer, which is basically a tris glycinate buffer. So here the pH is 8.3. Then you have a stacking buffer where the pH is 6.8, and then you have a resolving buffer where the pH is 8.8. So the glycinate ion which is present in your running buffer, so this forced to enter in stacking gel, and So in stacking gel where you have a pH of 6.8, the glycine will reach the deuteric ionic state, and then once it reaches the deuteric ionic state, then it will lose the force of electrophoretic mobility. And because of this, so there will be a force of stacking where all your protein will start dragging, and it will start sitting one over or piling one over the other. So in stacking, there will be electric force, which will allow you to move ahead. And then because of the deuterionic state of glycine ion, so it will drag it, and then there will be a stacking of these proteins. So once this particular stacking will go on in the resolving, so it will reach the transition phase of this resolving and the stacking gel. So once it reaches the transition, so there in resolving the pH is 8.8, and once it reaches there, so glycine mostly it assumes the negatively charged, and it starts moving or migrating at a very faster rate than the protein. So that drag force is removed, and then now protein is allowed to resolve based on the molecular weight. So in resolving, the protein will run based on the molecular weight, and then it will separate accordingly. So this gives the sharpness or the high resolution of your protein. So pH in case of SDS phase is very important. So you cannot afford to lose even a few decimal of pH, because even if a pH suppose 6.8, if you are taking 6.2 or 6, so that will be very clearly visible on the resolution of the protein. And when you stain it, so the intensity of the protein will be not so as you expect. So here you have to take into care that pH should be exact when you are planning to go for SDS phase. As exact the pH condition will be, so that much best the resolution of the protein on the gel will be. So this precaution you have to take. This is one table where the percent acrylamide which we have to prefer, and then the range of the protein which you are going to separate. For example, 15% acrylamide is basically used for 3 to 100 kDa protein, or when you are making a 12% acrylamide, so that is used for 10 to 200 kDa. So like this, there is a big table of percentage of acrylamide, and then what range of protein you can resolve. So we have to follow this also. This is one step of staining. So once your run is complete, so you have to go for staining. So here I have give you the basic information about the Comase blue staining. So here first you have to wash your gel, then you have to fix it, then again you have to wash it, and then you have to stain it with the Comase brilliant blue, and then you can destain it using the destaining solution. So typical protocol time, so it's almost half an hour. So within half an hour you can stain, and then another 10 minutes you can destain. Sometimes it takes more time, but then as you increase the time, so it will take more stain, and then ultimately you have to require a large volume of destaining solution to destain it. So you have to standardize this, and accordingly you have to stain and destain it. Similarly, we have another method, that is silver staining. As I told, this is very popular, and here you can see the silver stain gel. So here you can use this for the detection of 0.25 to zero point 0.5 nanogram of the protein present on your gel, and it will give you a very sharp and intense band appearance on the gel. So this silver staining, this is most sensitive method for the detection of the protein on the gel. So it is the deposition of metallic silver onto the surface of a gel at a specific location of protein band which is visible, and then easily you can capture this. So this is also very popular, but then it's time taking, and then a little bit tedious. So another is your fluorescent dye based staining. So nowadays this is very popular. So a lot of fluorescent dyes are available for the protein. So you can label your protein using different fluorescent dye, then you can run it on the gel, and once you have separated it, easily you can capture a single protein or a mixture of proteins. So as you wish, you can easily capture this, and it will give a fluorescence image like so appearance. So this is the beauty of fluorescent dye. The only thing is cost wise, this is the costliest method as compared to the silver staining and then Comase brilliant blue. So these are some of the methods which we are using for the staining of the gel. Last part is interpretation of results. So many a times when you are running, so you will miss, and you will get a very bizarre type of result which is very difficult to interpret. So some of these results I have tried to present here, like when you are using a very high current, so you can expect such type of cell. So there will be a zigzag like protein, and then it will be difficult to differentiate the protein bands. Or when there is a partial run, so any half of the gel you can expect the protein, so other half it will be a clear zone. Or when there is a diffusion of the protein, so you can expect such type of a balloon like structure onto the gel. So easily you can make out that there was a diffusion. Or if there is a very strange pattern of separation, so maybe at any direction, so in that case you can easily interpret that the gel has not been casted properly. That's why protein are running here and there on the gel. So easily you can troubleshoot. Or similarly, many times you can see different wells, so they are coinciding, and then your run also that are coinciding. So it generally happens when you are going to break the well which you are going to use for loading the sample. So in that case, so two wells that will be coincide, and then whatever protein you have loaded, that will coincide onto the gel. Or many a times you will get a lot of drag in the lens. So this dragging is basically because of the contaminants in your sample, especially the salt. So if there is a high salt in the sample which you have extracted, so that will leave you the dragging. And once the drag is there, the only ultimate solution is that you have to purify your protein using some column or some other method. And once you have purified and removed the salt or any other admixture, then you will get a very sharp and clear band. So I think briefly I have tried to touch upon all the steps which we are using in case of SDS phase in the most generalized way, with a hope that if you wish to try this, you can try using any sample. And then if you have any problem, you are always welcome. Anytime you can give a call, and then you can get our suggestions. So with this, I'll show you the video, and then we'll take up your queries, right? So we have one video. So this was made by one of my MSc student, Mr. Kankan Pandit. So last few days, so he is devoting almost 100% to design and to make this particular video. I think you all will appreciate this. So here we go.
Good morning, everyone. In this demonstration, we will learn the basics of SDS phase, that is sodium rhodyl sulfate polyacrylamide gel electrophoresis, and we will learn running of a sample in this gel, that is crude extract from pollinate leaf and stem. And at the end of the demonstration, we will visualize the pattern of different proteins present in the crude extract in the resolving gel. So let us start. The SDS phase system involves the use of an anionic detergent, that is the SDS. The SDS has following effects on the protein molecule. It breaks the hydrogen bonds among the amino acids in the protein molecule. It disrupts the hydrophobic interactions among different amino acids in the protein molecule. It prevents the aggregation of protein molecules. It linearizes the protein by unfolding it. And finally, and most importantly, it masks the uneven charge distribution among the amino acids and gives an even and uniform negative charge in the protein molecule. And in this process, each SDS molecule binds to two amino acids of the protein molecule, and thus leading to the formation of the negative charge in the protein molecule. In the process, when the SDS coated protein is run in the gel system, it achieves a linear relationship between the logarithm of molecular weight of the protein and the distance migrated by the protein on their molecular weight on the resolving gel. And using the calibration curve, one can determine the molecular weight of an unknown protein using the calibration curve. Now coming to the protocol, the total process can be divided into three parts. First, casting the gel. Second, running the sample in the gel. Third, visualizing the pattern of proteins on the dissolving gel in an illuminator. Starting from the casting of the gel is casted two times because it is a two gel system. First, the resolving gel is casted, then the stacking gel. For casting the resolving gel, we need distilled water, 1.5 molar 3 Celsius buffer of pH 8.8, 30% acrylamide bisacrylamide mix, APS and timid. And here we will use 2 ml of distilled water, 2 ml of 3 Celsius buffer, and then 2 bisacrylamide acrylamide mix, and then we will add 35 microliter of APS, and finally we add 10 microliter timid. The last two components, that are timid and APS, are responsible for the polymerization of this acrylamide and bisacrylamide through a mechanism known as free radical mechanism of reaction. And once the components are added, these are mixed properly and immediately transferred to the casting system using a pipette. And it should be kept in mind that during pouring, there should not be any bubble formation. And the length of the resolving gel should not exceed 2/3 of the gel casting system and should not touch the lower face of the comb. And after pouring, it is advisable to pour an amount of isopropanol. Adding of isopropanol prevents the direct contact of the polymerizing gel to the air, as well as the isopropanol helps to attain a uniform surface at the top of the resolving gel due to its weight. And it usually takes 5 to 10 minutes to solidify. Whether the solidification has been done or not can be checked by the leftover gel mixture in the beaker, and here you can see it is perfectly solidified, and we can proceed for the preparation of stacking gel. For preparation of stacking gel, we add 1.5 ml of distilled water, 480 microliter of acrylamide bisacrylamide mix, 1 ml of 1.0 molar 3 Celsius buffer of pH 6.8. And after adding these components, we halt and decant the isopropanol and wash the casting system with distilled water to remove any remaining isopropanol, and then again come back to the gel preparation. Now we add 65 microliter of APS followed by 20 microliter of timid, and the reaction starts. After mixing these components, we add the gel mixture to the casting system, and before adding, we should check whether the comb is properly inserted to allow the formation of even and uniform wells in the gel. And we add the gel in the system with the help of pipette without formation of any bubble. Usually it takes 10 to 15 minutes to solidify, and meanwhile we will proceed towards the preparation of sample. For preparation of sample, it should be kept in mind that the concentration of the protein in the sample should be uniform in all the samples, and the quantity should be 35 to 36 microgram, and it is standard to have a proper visualization in the resolving gel. And here we have already quantified the protein content, and we have taken the same content from all the samples. And after that, we will add a loading dye to the sample. A loading dye contains SDS. It helps to settle down on the protein in the well when it is loaded on the gel. After adding the loading dye, it is denatured at 90 degrees Celsius for 5 to 10 minutes in a thermoblock. while the stacking gel is being solidified. Once the stacking gel is solidified, that is checked on the leftover gel mixture in the beaker, we can proceed towards the next step, that is running the sample in the gel. For running the sample in the gel, we need 1x HDS phase buffer that contains tris base and glycine and the HDS phase apparatus. For running the sample, first we need to disassemble the gel caster and we will transfer the gel from the caster to the apparatus, and here we should do it carefully so that the comb should not be disturbed to avoid any disruption in the formation of the well or in the improper formation of the size of the wells, as well as the assembly should not be disturbed. Once the transfer is complete, then we add the 1x SDS phase running buffer onto the apparatus. It should fill the gap between the gel system and the apparatus, and also its tank should be filled partially with the SDS phase running buffer so that it touches the lower surface of the gel. Before removing the comb, it is good to mark the bottom of the wells with a marker for easy visual of the location of the wells during loading. Now the gel is ready to run with a sample, and our sample is also ready and to be loaded on the gel. And during loading the sample, it should be kept in mind that the sample should be loaded on the gel smoothly and gently so that the sample should not spill over the buffer, or it should not pass to the next well due to improper loading, and the sample should be properly loaded onto the sample with the identification mark and should be kept in a notebook during loading. Once the sample are loaded, we should load the marker. Here we use the page marker to the leftmost well of the gel. We use 4 microliter of the marker and loaded onto the well. We are ready to run the gel. The power pack is turned on. The electrodes are connected properly to the cord, and the cords are connected in proper orientation and in proper place. Power pack. Now we are running the gel. It usually takes 2 to 2.5 hours to run completely the gel, and once the gel run is completed, we disassemble the gel apparatus, take out the gel and wash it with distilled water. It should be kept in that the glass plate, the ceramic glass and the spacer should be in their proper position while disassembling. And after washing, the stacking gel is separated from the resolving gel because it is of little use or no use for resolving and visualization. And after stacking gel is separated, a resolving gel is taken out from the ceramic plate using the spacers and then kept in the tray for staining. Now we are proceeding towards the visualization step. The gel is stained with a staining solution that contains Homer's brilliant lower 250 stain that contains methanol and glycolacetic acid. To stain the gel, it usually takes 2 to 3 hours in a shaker. After staining is complete, the gel is need to be destained. The destaining solution contains 1:1 volume of methanol and water, to which 10 ml of glycolic acid added to make a total volume of 100 ml, and this solution is used for destaining. To destain the gel, it usually takes 2 to 3 hours or it can go up to 10 to 14 hours. That means it should be kept for overnight. So this training should be done until the bands appear permanently in the almost transparent gel. Once it appears, the restaining step is complete. Now we'll visualize the gel. For visualization, the gel is placed on a white light illuminator. The illuminator is turned on and we can visualize the prominent bands of protein on the gel, and the disease phase gel run is complete.
So we have with us Mr. Kankan Pandit. So he is in our group, and congratulations, Kankan. So really, it's appreciative. So
Thank
this
you, sir.
first time I have seen this because of busy in other work, but really it was really good.
Thank
You have nicely explained different steps, and even capture was perfectly done. Thank you, Kankan. Thank you. So
you,
now
sir,
if
for
you,
the support.
yeah. So now if you have any queries, any questions, please ask. Please interact. Any queries, anything you want to ask from this particular part. So as usual, I think so we don't have any queries. So what we'll do is even later part also, if you have any queries during your experiment, you are always welcome to give a call and we'll love to answer. If you know, definitely we'll answer. So anytime you can call us. So I think SDS phase we have completed, and sorry for KBK partners because I know it will be a little bit difficult to grasp this, but then this is very important and a common tool which we are using in our lab, especially biochemist and molecular biologists. With this, we have completed our first part, that is SDS phase. So now second session is an invitee talk. As I told, so for today's invitee talk, we are fortunate to have Dr. Vinutha T with us. So let me briefly introduce today's speaker, Dr. Vinutha T. She is with us. So she has done BSc and MSc from University of Agriculture Science, Bangalore, from 1999 to 2006. So now we three are from same US Bangalore as a alumni. Dr. Mohan Chauhan, Dr. Vinutha T, and myself. So we did at different intervals, but then we are alumni of US Bangalore. Then Dr. Vinutha T, she did a PhD from Indian Agriculture Research Institute from this division only. And then she got gold medal also for outstanding PhD thesis. So this is really remarkable, getting gold medal from Indian Agriculture Research Institute. And then she is working in the area of this nutrition only, as I told, and then she got several awards like Young Scientist Award, Young Associate Award, etc. So there is a big list. She published more than 50 publications in the Dr. Sanjay Jain Saab, can you please mute yourself? Yes. As I was telling that she is working in the area of nutrition, especially in soybean, and then she got several awards to name a few like Young Scientist Award, Young Associate Award, etc. And then she also was awarded DBT Best Poster Award in the year 2019. And it's not only this, so she has 3 patents under her feather. So she submitted 3 patents. One is on vitamin E extraction, other is on hydrothermal treatment and near infrared in case of pearl millet for enhancing the shelf life of the flour. And third is gluten extraction and regeneration protocol. So she had already got 3 patents at such a young age. So with this brief note, now I invite Dr. Vinutha T to please give today's talk on the topic development of technologies for enhancing the keeping quality of a pearl millet flour. Dr. Vinutha,
Thank you so much,
please go ahead.
Ranjan sir. I'm really deeply, happy to have this forum here to give a talk on the processing technologies. And I congratulate Ranjan sir and Archana Sachdev ma'am and Suneha ma'am, who have really taken a so much of efforts to make this training program the very first time in the online platform. So with this, I share my slides. Sir, can you enable the slides to share?
Yeah, just 1 minute. Yeah, please go ahead.
Can you all able to see my slides?
Yes, please go ahead. Please go ahead.
A very good morning to all of you, to all the trainees who are here to learn and from Division of Biochemistry, what and all the research it is going on here. And especially today, we are going to talk on, I'm going to give a talk on a novel processing techniques to reduce the rancidity and improve the dough quality of pearl millet flour and its effect on nutritional quality and functionality. So if you come to the pearl millet, you have already been, several people have already been given a talk on this, that it is rich in nutrition. Yes, certainly the pearl millet has all the goodness of nutrition. If you see, it has higher protein content, high PUFA content, high iron content, zinc content. If you come to the essential amino acids also, it has a good amount of methionine content, where the many of the time the quality protein which lacks this methionine in it. And it has a good amount of that, and also it has a dietary fiber, and it is a very important to maintain or the regulate the glucose levels in the blood. So despite all this goodness of nutrition, if you see that pearl millet doesn't it prone to rancidity, in the sense that once you make a flour and keep it in the room temperature for the 10 days, so after 10 days you feel like a foul smell in the flour. That is because of an higher lipid content in the flour. It is readily getting oxidized to give you a off flavor formation. So other problem in the pearl millet is that poor dough quality. If you see that it has all the goodness of nutrition, no doubt it is superior than the wheat with respect to the nutrition, but somehow it is not acceptable by the consumers and also by the industrial people. Why? Because one is rancidity, another one is the poor dough quality. But because of this, like you, unlike wheat, if you see the wheat, like thousands of recipes you can make out of the wheat flour or wheat products, but the same thing will not hold good for the pearl millet, and it cannot. That is the only problem here. These are the two problems where you can see that pearl millet products are not on the plates of the consumer because of these two reasons. And let us see first what is rancidity. So it is already must have been mentioned in the many of the talks that because of an higher lipid content, the rancidity causing enzymes like lipase which ox on the lipid content, and it oxidizes the lipid to a free fatty acids, and these free fatty acids will serve as a uh, substrate for the lipooxygenase, another rancid causing enzyme. And this lipooxygenase in turn, it will oxidizes the free fatty acids to give you a primary oxidative products like lipid hydroperoxides. And these lipid hydroperoxides further, it is non-enzymatically get oxidized to give you a secondary oxidative products, and these secondary oxidative products will form an adducts by combining with the protein or with the nucleic acids, and again it will also lead to a modified proteins or the modified DNA, and again it will also leads to a lipid peroxide formation or the off flavor formation in the flour. So once these lipooxygenase, when it acts on the free fatty acid content to give you a hydroperoxides, and these lipid hydroperoxides further it will act as a new substrate for the two other major enzymes, the rancid causing enzymes like peroxidase and polyphenol oxidase. And these two enzymes which acts on hydroperoxides, and it will releases again secondary oxidative products, and also free radicals. And these free radicals in turn, it will directly attack on the free fatty acid content, which is a product of a lipase oxidation. And again, this chain will go on, it will continuously, it will goes on if the lipid content in the food or in the flour it is higher. And this is how the rancidity it occurs in the pearl millet flour. So if you have seen the oat, because we all will consume the oat today, like oatmeal or a oats, it is really popular, but oat is not our country's food, isn't it? The oat is also having the equally that much percentage what the pearl millet is having, that is 5 to 6% of the lipid. But in spite of that, if we are consuming and we can able to keep the oat for the longer time, why can't the pearl millet? So in this direction we also have tried. And here in order to enhance the shelf life of the flour, or in order to reduce the rancidity in the pearl millet flour, we have optimized the thermal treatments. And it is a combination of thermal treatment, it has been given in a 3-step protocol to arrest the rancidity. So let us see what is this protocol. So this is, initially we have gone for the hydro treatment or a soaking treatment. So the soaking or hydro treatment, though it looks very simple, but it has enormous biochemical changes. It can influence the changes in the biochemical processes. So through soaking, what will happen? All the tissue will get hydrated. Because of the hydrated tissue, or the tissue, if it has an higher content of the protein, obviously there will be a higher content or higher activity of the enzyme at but that particular temperature, whatever may be the prevailing temperature. If you are increasing the moisture content, or if you are increasing the hydration of the tissue or the grain, and naturally there will be an increase in the activity of the enzyme. So in order to with this background, what we have done, we have soaked for certain period. And this is we have done only because in order to activate all the rancid causing enzymes through soaking, so that further thermal treatments will efficiently, it will cut down the activity of the enzyme. So next, what we have done after that, with the moisture content of 33%. So everywhere that I have mentioned the moisture content, because the moisture content is equally important to denote the product or the food quality. So here with the moisture content of 33%, then we have gone for the coarse grinding of the pearl millet grains, and with the particle size of 2.5 micrometer. And this coarse pearl millet flour, now it was subjected to a hydrothermal treatment, where it maintained the temperature of 100 degrees Celsius. And this treatment was particularly given for the 5 minutes. So why 5 minutes? Because the flour, the appearance or the visibly the color of the flour will get changed if we are giving more than 5 minutes. So therefore it was optimized for the 5 minutes with a moisture content of 24%. So this step, it has been included here, it is optimized here in order to inactivate rancid causing enzymes. So once we have inactivated the rancid causing enzyme, the next step or the next question is that how to dry the flour. When it is having a 24% moisture content, we need to dry it to bring down the moisture content according to the Codex Committee. The Codex Committee is a world leading committee where they decides what should be the moisture content for the each and every food product. For the flour material, they have decided, or they have given a certain moisture content range that should range between 10 to 14 or below 14%. So in order to bring down the moisture to 10%, so what we have done, we have gone for the rapid drying method. Unless the conventional method, we have gone for the thermal near infrared rays treatment. And these thermal near infrared rays, they are available in the range of zero point 0.7 to 1 micrometer wavelength. And they are very, very, the rays, the penetration of the rays is very, very high, so that it will directly penetrate into the every particle of the flour. And therefore it will help us in the it will help in the drying of the flour. So this treatment also has been given at 40 degrees Celsius for the 5 minutes. And then after, once we have bring down, this 5 minutes has been set only. Yes, the 5 minutes has been set only because, not because that what is to see any other changes in the flour due to thermal near infrared rays treatment, but this 5 minutes has been set or optimized only for the moisture content. So the level of the moisture content, once it is reduced to a 10% or 11%, so the infrared rays treatment has been stopped here. So later on, that coarse ground material flour was again fine ground to get a particle size of 0.5 micron. So this particular whole process is now under patent. So after giving all this thermal treatment, the next question is what will happen to a rancid causing enzymes. So if you see there are four rancid causing enzymes. They are present. One is lipase, another is lipooxygens. If you see, there is a substantial decrease in the lipase content and also in the lipooxygenase content. If you see the peroxidase and polyphenol oxidase, it is almost nil. It is almost nil in the activity of these two enzymes. So this we have done for a different treatment, like individual treatment of hydrothermal, and hydro treatment is nothing but a soaking, where you could see that increase in the lipase activity during the soaking time, and there is a decrease increase in the activity of lipase during soaking, and also polyphenol oxidase activity has also been increased during soaking. So this particular two enzymes activity has been increased because they are optimum, or the activity is maximum when the temperature, the prevailing temperature which was given was 30 degrees. So therefore, both it is a moisture content dependent or hydration, as well as the temperature dependent manner, the activity of enzymes will be there. So later on, if you see that compared to an individual treatment of hydrothermal and near infrared treatment, the combination treatment has substantially reduced the enzyme activity. So next, what we have done is that then once we have given a thermal treatment, and that flour was stored at room temperature for several days, 90 days. So here, if you see from the days of storage, that is 0, 10, 20, 30, 60, and 90 days, so the primary oxidative the hydrolytic rancidity, in the sense the accumulation of free fatty acid content was drastically reduced. That is, there is a reduction in the 90% of hydrolytic rancidity due to the thermal treatment. And if you see in the 90 days, it is almost 68% reduction in the rancidity was occurred. So now next comes to the another thing is that how to reduce the oxidative rancidity. Here also, after thermal treatment, when the flour was stored for several days, you could able to see here the oxidative rancidity was drastically reduced to a 98%. And similarly, at the 90th day of storage at room temperature, the oxidative rancidity was reduced to 66%. It is obvious that the reduction in the rancidity was expected due to the reduction in the enzyme activity in the pearl millet flour. So this again, once we have done this entire experiment in the Dhanshakti varieties, so later on we also have uh, replicated this particular treatment in several zonal varieties of the pearl millet, and we could able to see the similar trend in the reduction of hydrolytic rancidity and also in the oxidative rancidity. And again, based on this, we have developed a rancidity matrix model, and here you could see all this red, orange, or green zone. It shows the different level of rancidity. For example, green zone shows the low rancidity region, and orange, the color, it denotes a medium range rancid, and red region is a high rancid region. So after hydrothermal treatment or the combination of the treatment, when the flour was stored for 90 days, you could able to see the shift in the rancidity matrix model from orange or red region to an entirely green zone, or it is a low rancid region. So this means it is possible that irrespective of the material or irrespective of the genotype, this particular treatment is able to, or significantly, it is highly efficient to reduce the rancidity or arrest the rancidity in the pearl millet flour for the 3 months. You can keep now the pearl millet flour for 3 months at room temperature without any rancidity in it. So later on, what was our main aim was that once we have reduced the rancidity from the thermal treatment, what happens to a molecular or structural changes which occurs in the starch and protein is very important to study, because these changes will lead to a changes in the nutritional quality. So therefore we wanted to see what are the changes, or what is the changes in the starch and protein properties due to the thermal treatment. Initially, we have seen the changes in the starch properties and increase in the enzyme activity as a function of hydration of grains during soaking. And these are the images. What you are seeing is a CLSM, that is a confocal laser scanning microscope images, where you can see the intact starch molecule and with the smaller sized starch granules under non-soaked condition. Under soaked condition, the swelling of granules you could able to visibly see. So what we have observed is that the swelling power has been increased and starch solubility was also got increased during soaking, and thus it also lead to a ordered crystalline structure molecule of the starch when we have analyzed through an FTIR. The data here is not shown. And then the moisture content also, we have seen that the moisture content was around below 40% or below 35% during duration of the time, and the soaking hour was optimized for 1 hour.
Can you please mute yourself, analyst?
The soaking hour was optimized for 1 hour.
Yeah, please go ahead, Vinuta. Yeah, Dr. Vinuta, we are not getting your voice.
We're not able to hear you.
Yeah, that's right. So I think there is some technical glitch.
Because after 1 hour we could not and
Yeah, Vinu, there was some problem in your voice, so it was not audible.
okay, sir. Again, I am sharing my
Yeah,
slides.
please.
Yeah, could able to see my slides. So next, what we have seen is that there is a structural changes also has been observed during the thermal treatment in the flow matrix of the pearl millet. And this is what the FTIR graph it looks like, where we could see that these wave numbers which are mentioned here, that 1047 by 995, which denotes the order crystalline structure, and similarly 1022 by 995, which denotes the amorphous to crystalline region. So where we could see that this the below line is a HT region, where the pearl millet flour which is treated only with the hydrothermal treatment, and this is the flour which is treated only with the in combination of hydrothermal and near infrared rays, and this is with only with the THNIR. So what it is showing, this is a control. The green region is a native flour, where you could see that there is no much change in the crystalline structures or the order crystalline structure of the starch when it is treated only with the near infrared rays treatment, but the drastical changes or a decrease in the order of crystalline structure of the starch was very well pronounced in case of hydrothermal treatment, and also to some extent in case of a in combination treatment. So this you could see that the ratio of 1047 to 1022, it was higher in case of near the ratio of 1022 to 995, which was higher in case of hydrothermal treated flour as compared to rest of the treatment. And this shows that there is a disruption of the starch molecule. It had occurred, the ordered crystalline structure of the starch got disrupted. Because of this disruption in the starch molecule, it has enabled or it has allowed the amylase enzyme attack, in the sense that amylase enzyme, which is more prone now. This particular treated floor is more prone to an amylase attack, and because of this reason you could able to see there is a higher starch digestibility. It was highly pronounced in case of hydrothermal, only hydrothermal treated floor, as compared to a individually treated, near infrared rays treated, and in combination. So this is because of the changes in the order crystalline structure. And similarly we could able to see that there is no much change in the protein digestibility, although there was a 3% decrease in the protein digestibility was observed in case of a hydrothermal treated flour as compared to two other thermal treatments. And this could be due to an aggregation of the protein which might have occurred during the thermal treatment. So this is what, again, this data which is also been supported by a CLSM images of confocal images of starch and the protein, where the green regions are showing the starch molecules. You could see that the packaging of the starch granule, it is very, very compact in case of a native flour as compared to a treated flour. Here, this is a hydrothermal treated, this is a near infrared rays, that is in combination. So what it is showing is the intactness or the compactness or the packaging of the starch granules got disrupted here in case of a hydrothermal treated, and also the size of the starch granules has also been decreased as compared to a native flour. And these are the two reasons where you could see that it will enable the higher alpha amylase activity, or it can attack of alpha amylase activity is higher because of a less compact nature of the starch granules, and also because of the smaller sized starch granules, which has increased the starch digestibility in the thermal treated flour. And again, if you see, the denaturation of the protein was higher, in aggregation of the protein was higher, where you could see in the CLSM image the hydrothermal treated proteins, where you could see an higher aggregation of the protein, and this in turn it has enabled the decreased protein digestibility. And we also have seen the dynamics of starch, protein, and lipid yield as a function of thermal treatment, where you could see there is a decrease in the yield in case of the starch, and here in case of hydrothermal treated flour. So that this is very well it happens because the yield of the starch and protein may vary depending upon the arrangement of these molecules in the flow matrix. And similarly, the pasting properties will also significantly got varied, where if you see the pasting temperature, it is decreased in case of a thermal treatment. So that means it's showing that the temperature decrease in the temperature, it is showing that this much temperature is enough to disrupt the, you know, the floor matrix to give a viscosity or the pasting properties. And this is due to the decreasing temperature is mainly due to the disruption of the starch granules or disruption of the order crystalline structures, and the amylopectin molecule disruption was more. Because of this, it took less temperature to get the pasting formation, the paste formation. So similarly, the peak viscosity has also been drastically reduced. If you see, there is 67% reduction in the peak viscosity. So this is very well, it has been shown in the disruption in the crystalline structures. And that's how it also has shown a higher amount of starch digestibility. If it is higher the viscosity, lower the digestibility. So all these parameters, whether it is peak viscosity, where pasting temperature, final viscosity, setback viscosity. So the setback viscosity majorly it will denote the retrogradation of the starch, and the breakdown viscosity, where you could see the lower breakdown viscosity was seen. So this is somehow something which is really interested in case of a food industry people, where they wanted any product, it should have a lower breakdown viscosity, so that the product made out of it will be stable for a long time. So whole this concept was conceptualized, where you could see that the hydrated grains matrix shows an higher content of higher activity of polyphenol oxidase and lipase activity, and similarly the increase in the protein solubility was there. If you come to the hydrated starch matrix, where you could see that the increased starch solubility and the increased swelling of the starch, and the size of the starch was being increased, due to which there is an ordered crystalline structure was observed in the hydrated grains, and where you could also see, due to increased protein solubility, and the FTIR also has seen the increased alpha to beta ratios. And once these hydrated grains wet flour, when it is subjected to a thermal treatment, where you could see the decrease in the rancid causing enzyme activity, and this was highly pronounced in case of a combination treatment as compared to an individual treatment. And whereas this decreased order crystalline starch molecule and the viscosity as well as alpha to beta ratio, these all are decreased, and it was highly pronounced in the hydrothermal treated flour as compared to an in combination treated flour. So this whole now result, this has now been food chemistry. So next we will also see the techniques to improve the dough quality of the pearl millet flour. This is how the gluten network in the wheat dough. You can see that the gluten is made up of two protein, glutenin and gliadin, and upon hydration, these two proteins will form a network in the dough, and that's how you see the dough pliability and the elasticity. The major parameters which are important for the dough quality is the gluten networking. So based on this principle, the vital wheat gluten, it has been extracted from a wheat and it was regenerated in the pearl millet flour. And this particular extraction methodology has also been now under patent, and its regeneration in pearl millet is also now under patent. So these are the different patents you can see in the site, where they have done a lot of work on the vital wheat gluten extraction. But every patent has its own advantage and disadvantage. So based on this, we have optimized the protocol for economically feasible protocol to extract vital wheat gluten from the wheat flour. And these are the different steps where you are seeing where we have extracted the vital wheat gluten, which is under patent. So what is the quality? How to analyze the quality of the vital wheat gluten? There are two important parameters which are really important to analyze the quality of the vital wheat gluten. One is water absorption capacity, another one is an elasticity, that is measured under texture analyzer and in the form of stability. So these water absorption capacity, if you see, there are several drying methods we have used to dry the the vital wheat gluten elastic mass. This is an viscoelastic mass, and the drying is a tricky part. And we have used a different temperature condition. Also, we have used thermal near infrared rays treatment, and also we have used high temperature and low temperature. Low temperature here I'm calling 40 degree. So when we dried a vital wheat gluten and 40 degree. So this has given an highest water absorption capacity where compared to the rest of the drying methods. And this also has been, when we have compared that with the commercially available vital wheat gluten, so the gluten extracted from our optimized protocol has shown an higher water absorption capacity. Similarly, the gluten extensibility, if you see the gluten extensibility here, the gluten extensibility also has been shown a significantly higher gluten extensibility in the extracted vital wheat gluten as compared to a commercial one. So now the question is, once we have extracted the vital wheat gluten, we have to regenerate into a pearl millet flour, because pearl millet has a poor dough quality. But it's not so simple to mix two different things and make a dough, but it has its own, we have to optimize it in a proper way in order to get a dough quality as superior as wheat. So these are the different parameters we need to analyze, that is through either through a ferinograph or through a mixolab instrument, where we have analyzed the 5 different parameters like water absorption capacity, dough development time, stability of the dough, mixing tolerance index, and dough consistency. In all these parameters, which were on par with the pearl millet flour when it is regenerated with the vital wheat gluten of 7%, and now it is being standardized with that. And again, we also have to see that the functional characteristics of the dough in terms of hardness, adhesiveness, cohesiveness, springiness, and these are the four different parameters which are required for the mouth feel. In the sense that moment we eat and how we feel, so that will be designated by these four parameters, and these four parameters can also be analyzed by a texture analyzer. And again, the dough extensibility is one of the important parameter, so that the elasticity to the dough is important. At the same time, the viscosity in combination with elasticity is also equally important. So here we see that the dough extensibility was good in case of the dough, in case of 7% VWG pearl millet flour. And again, it was also, we have seen the rheology of the dough through analyzing the viscoelastic behavior. And these are the mechanical spectra depicting the viscoelastic behavior of the pearl millet flour when it is reconstituted with a vital wheat gluten. And these G prime and G double prime, where it indicates the elasticity and also the viscosity. So here, the linear viscosity region of the different dough sample you could able to see here. This we have studied by means of a stress sweep protocol. So in comparison to wheat dough, the similar strength of the linearity over the entire frequency range for the storage and loss modulus was, in the sense, the elasticity and viscosity modulus was observed here. And this, as lacking in accentuated inflection points, is very very important in order to analyze the dough quality as a superior dough quality. So all these parameters, finally it says that the 7% VWG regenerated pearl millet flour, it has a good dough quality. So this also, the entire thing now it is being also communicated to a food hydrocolloids, where we could see the several other contents I'm going to cover of this part in 11th of March, where we also have to see that in the next hour. So now, what is the potential of the technology? Yes, we have extracted the vital nutrition and we have regenerated that in the pearl millet flour to make it as a quality dough. So the potential is that India, we all know that it is a second largest producer of the wheat in the world, and it has a cutting edge advantage in export of wheat byproducts like VWG. There are two wheat byproducts you can see. One is gluten, another one is the pure starch. But the pure starch drying and making it to a resistant starch is one of the huge or biggest industry which is there. And all the resistant starch and vital wheat gluten currently we are importing from Germany, China, and several other, Australia and several other countries. So because we doesn't have that cutting edge economically efficient technology where we can make our own byproducts from the wheat, though we are the largest producer of the wheat in the world. So this cutting edge advantage in export of wheat byproducts like VWG at premium price by adoption of this technology at upscaling level. The another in is this product developed as the potential to move as a sustainable alternative to wheat in many baked and cooked preparation as a new staple food, owing to its easy availability through a local market, supermarkets, and e-commerce site. So this we have already done. This product has been commercialized, and this product not only can give a positive impact on these markets but also has the potential to address the nutritional challenges, as the hidden hunger and malnutrition, if you see, it is associated with a huge investment from the Indian government with the estimated economic cost of 0.8 to 2.5% of the total GDP, which is equivalent to 15 to 46 billion dollars. So you just see that how the government is spending so much of money to eradicate the malnutrition or to address the hidden hunger. And also these things will really will make us to think in this particular direction, how to make our country sustainable by giving so much of efficient, economically efficient technologies what we have given here. And now it is available and in each and every consumers can buy this, and this has been commercialized to a private company. And this happened only because of the leadership of Dr. Shalli ma'am, head of the division, and also with our team members, Dr. Suneha Goswami, Dr. Ranjit Ranjan, and Dr. Shalini Gaurudra. So together, as a team, we could make out this product and it now being commercialized. So I want to thank each and every one of team member here for their support to carry out this work. Thank you all.
Thank you, Dr. Vinutha. So now if you have any queries, please interact. So I request all the panelists, if you have any questions, any queries, anything to discuss, please ask, please interact. Yeah, no queries, no questions. Anyway, still if
Was
you
good
have,
presentation, Dr. Vinita.
Thank you. Thank you, Mohan Chavan. Happy to see you here.
Yeah, I too see.
so anyway, I think so. Still, if you have any queries, please leave it on my chat box, and then Dr. Vinutha, she will have to answer later on.
Sure,
So
sure.
yeah, so I think you all will agree that she has nicely sketched different aspects of technology which we developed here at a division of biochemistry IRI, and she is one of the very active member of that particular team. And as I explained that she has already done 3 patents under her feathers. So and she nicely explained different aspect of the technology, different uses, and then a basic information about all those technologies. So Dr. Vinutha, thank you for sparing your time and giving such a wonderful talk.
Thank you, sir.
So all panelists, I'm sure they have enjoyed your talk. And we have YouTube also, so that will share, so that later on also, if you wish, you can go through these talks, and then you can get maximum benefit out of this. So with this brief note, now we are at the last part of our today's schedule, that is practical. Again, Dr. Vinutha, she is going to organize this particular practical, that is on assessing the protein digestibility and bioavailability assay in pearl millet flour. So Dr. Vinutha, now floors is yours.
Yeah, thank you, sir. So I'm just again engaging all of you to how to analyze the protein quality or through in vitro protein digestibility. So let me first share the uh, slides so that the will make the principle clear first.
अभी वो रूट की सोच रहा हूँ सर, तो कौन कौन से एक्सपेरिमेंट का रूट स्टिक मतलब रूट स्कैनर से लेंगे हम, पता लीजिए आप
जो ट्रांसक्रिप्टोम वाले सर हैं,
FT2961 होगा।
Not able to share my slides. Ranjan sir, Sunay ma'am, give me 5 minutes. Let me check what happened. I'm not able to click. Any folders are not opening. I'm just getting
please
the
please check out, please check out, no issue.
starter is very less charging.
So by the time any of the panelists, if you want to put something before us, so please, you are most welcome. Or if you want to share anything, any experience, any comment, any suggestions.
Sir, I'm back. Wait a second. I'm just doing this. Maybe charge is very less. I don't know what is the reason.
Sir, hello. No, your mic is mute, sir.
Yeah, please tell.
Yeah, for the starch digestibility kinetics, earlier, Madam she shared about the phase-wise digestion. Instead of that, can we have a spiral digester? Can we design kind of a uh, spiral digester kept in a different temperature and then allow the sample to pass from one side to another side and get the digested compound and estimate in between we can have the outlet to take out and then do it.
Yeah, Mohan, actually few groups, they are already working on this particular aspect. Giving a hypothesis and then making it practical. So there is a large gap between these two. So Dr. Suneha and Dr. Vinutha, so along with Dr. Veda also, so they developed this sequential method for the enzyme activity and then for the viability assay. But then what you are telling, that is spiral based method, so it will take time. I think yet few groups they are working, but exactly I don't know the status,
Because
so they will be the right.
I worked on one of the like chondrian digestion,
Hmm.
and our group got published the paper. We are now thinking of like making a spiral digester like same way as it is happening in the intestine.
That we can, that actually
Yeah,
that should be the right way basically.
yeah, that's what.
That should be
So
the right.
where the surface area can be increased, and then we can think of increasing the digestion and check whether how exactly the in vitro happens.
Exactly that should be the right way, but let's see, it will take time. Yet we don't have any model like this.
Okay.
Dr. Vinutha, so sound is not there. Can you please check that sound?
Ranjan sir,
Yeah,
sir, can you able to hear me?
yeah, please.
Okay. So today we will see actually some problem technical glitch in my laptop, and I came to Dr. Sneha's room. Here I am just giving you the just a brief on why we need to analyze the protein quality. Why it is so important? Because if you see the malnutrition, it is an alarming problem in the world. Not only in the world, if you see that more than 50% of the children in our country they are malnourished because of improper intake of the protein and other vital nutrients. So with this, so if you see undernourished people in the world, there are it is going to increase by 2030 to 841 million people, and that so the protein deficiency has two major problems. One is wasting, another one is stunting. So if you see the stunting means it is a proper height to a weight, and wasting means improper weight to the height. There is an higher height but lesser of weight, and stunting is lesser height and higher of weight. And these are the two major problems if you see in all the almost more than 50% of the children in the country, and this is due to a protein deficiency. So 47 million people in the country they are wasted, and 144 million kids in the country they are stunted. So this is what due to the COVID-19 pandemic issue, if you see that 6.7 million additional children right, are suffering from wasting. You just see the alarming increase in the population where you could see that so much of malnutrition or the nutrient deficiency which is causing not only the physical appearance will get changed, but the mental ability also will drastically reduce. Once the child will attain an adult stage, he could not able to think, he could not able to do, he could not able to focus, and he could not able to, excel in his field, whatever may be the field he or she will take. So this is majorly because of 90% of the time because of the in the sense that improper nutrient intake, especially at the age of 5. So whoever may be the kid, if they take the proper nutrition below age of 5, so certainly their overall physiological growth and the mental growth will be optimum. So India is home to most of the number of malnourished children across the world, and there are several. The 8% of the deaths of the children below age of 5 in India, according to UNICEF data, is because of the malnutrition. So if you see several initiatives that government of India has taken to address the nutritional problem, but still it has become a distant dream for the Indians how to achieve the the malnutrition or address the malnutrition problem. So this is some of the basic what I wanted to know you all of you, and why we need a quality protein. So this background is given just to make you all alert, that aware that what is really going on in our country. So let us see what is quality protein. Quality protein is majorly it is dependent on the two factors. One is amino acid composition, another one is digestibility of the protein, how the digestibility of protein by pepsin, trypsin, chymotrypsin, it occurs and it gives the free amino acid, and again it gets absorbed in the intestine, and how much it is bioavailable. So that is what bioavailability of the amino acid is also important, and then we will see the digestibility, how the food digestion pathway at different phases. That is in the mouth, if you see at the pH 5 to 7, there are several
several enzymes like amylases, salt, and biopolymers, carbohydrates, proteins, and lipids. And in the mouth, maximum we will be chewing around 5 to 60 seconds, and then it will reach to a stomach where the pH in the stomach is maintained at 1 to 3. Then the several enzymes like trypsin, chymotrypsin, hepsin is there, and here also 30 minutes to 4 hours any food it stays in the stomach, then it will enter into small intestine. There also several enzymes are there. Those enzymes will again further digest. Then it will be absorbed by a small intestine. So next we'll see that why the protein quality is important. If you see the international and local government regulatory bodies throughout the world have introduced the standards by which the quality of the protein in a food product will be judged for completeness to delivery of essential nutrients which are needed for the human growth and sustenance, and also the digestive percentage of protein distribution. So the quality of the protein is judged from the regulatory standpoint as a function of efficiency of the protein digestion multiplied by the presence of essential amino acids. So if you see most of the time, the essential amino acids out of all 9, we always lack either lysine or methionine. Rest of the 7 amino acids are really we need the amount, at least in the more than 60%. But if you see for the methionine and methionine, which is one of the essential amino acids, is completely or it is very, very low in case of pulses, and the lysine, which is very, very low in case of cereals. So the complementing cereals and pulses can also boost the quality protein by intaking almost all the essential amino acids. So let's see the principle it works, and this is the principle where you see that the protein actually it will be digested by a for 37 degrees Celsius. Later on, this is a gastric. This we are mimicking the digestion pattern which you see in the human. This is a gastrointestinal mimic model of the in vitro protein digestion, what we are seeing today. So this is a gastric digestion by externally adding in the pepsin. He has maintained was 7.4 at 37 degrees Celsius. Later on, in the intestinal digestion, the trypsin and chymotrypsin will be added at pH 7.4. Sorry, the pepsin pH is 2. Sorry, it is not 7.4, it is 2. In the stomach, the pH of the stomach will be 2, and that too for the pepsin, it is the ideal pH so that it can hydrolyze the protein. You see the protein gets hydrolyzed to a peptide amino acid at pH 2 at 37 degrees Celsius, and then followed by a trypsin and chymotrypsin digestion. Again, it will undigested protein which is present by the pepsin will be rehydrolyzed by a trypsin and chymotrypsin to give you again the free amino acid. So undigested proteins are removed by a precipitation with the PCA. Amine groups of the amino acids will be estimated by a Nim-Hydrin reaction where it will form a Rumen's purple color. So the amount of Rumen purple formed in the reaction is proportional to the amount of reactive amino acid. In the sense, it is proportional to the amount of free amino acids present in the test tube, and that can be read as a spectrophotometer at a wavelength of 570 nanometers. So later on, it will be corrected for the relative reactivity of certain alpha amino acids as an in vitro digestibility score. This can be calculated. So let us see what are all reagents we require. So we require Nim-Hydrin reagent, hydrochloric acid, PCA, and the tris buffer of pH 7.4, and sodium acetate, reagent alcohol, and then we will move to a gastric and intestinal digestion. So this is what the gastric and intestinal digestion will be done in the lab at in vitro condition. So where you have to add 90 ml of HCl, and then for the 0.5 gram of water, and then mix thoroughly, but then incubate at 30 minutes at 30 seconds in an airtight shaking incubator at 300. Later on, you have to add 1 ml of pepsin. This is 1 mg per ml, the concentration. Then mix thoroughly. Then again, you have to incubate this pepsin added mixture in the 37 degrees Celsius at 60 minutes with the RPM of 300. After the incubation is complete, remove the samples and adjust the pH to 7.4 by an addition of of 2 ml of 1 molar crystal, which we already, you have to prepare it as CA7.4. So then again you mix it well and vertex it. Now you add 200 microliter of crystalline thymosin. Again the concentration of enzyme is 1 mg per ml. So mix thoroughly and incubate that for the 4 hours at 37 degrees Celsius in an air shaking incubator. The RTM test was 300. So at the end of the crystalline thymosin incubation, place the samples in boiling water for 10 minutes so that you can inactivate all the enzymes present in it. So once you have inactivated all the enzymes, remove the samples in the boiling water and again you mix it by vertexing. Then allow to cool it for 20 minutes. Now you add, you take the 4 ml of each of this sample and you go for the centrifugation by adding a CCA. So that whatever undigested protein will be there, that will get distributed. So the digested protein will be there in the supernatant. Now use the supernatant for the mean hygiene assay and you estimate the amine concentration with these formulas, where you also want glycine sandwich. This in detail we can see in the video. So this is a primary amine concentration you have to estimate. Then you go for the primary amine concentration corrected for dilution in days. You have to go for it. And next, you have to analyze the in vitro protein digestibility using the formula as given here. So in detail, we will see this in the video. So where the in vitro digestibility is nothing but the amine concentration which you have calculated through the Neilson assay, and you have to also add the total amount of protein you have to take into consideration and the total amount of protein which is undigested, that also you have to take into consideration. So overall, you can get an in vitro protein digestibility with this formula, where you have to plot several graphs to get the intercept of the y-axis. So that also you need to include in the in vitro protein digestibility, and the conversion factor also you have to include. So with all these things, you will get an in vitro protein digestibility percentage. Once it is multiplied with the lowest essential amino acid content, then it will give you a PDCAS score, that is protein digestibility corrected amino acid score. So that score will be always 1 for the egg and milk protein, and below 1 is PDCAS value. If it is below 1, that means it has a lower quality than chicken protein. So these are the protein quality. In the same way we did it for the pulses, and also we have did it for the pearl millet. Also we have seen the percent daily value of this most limiting essential amino acid like methionine in pulses, and also in the pearl millet. So this is the pearl millet methionine content. If you see the all blue region, it has a decent amount of methionine content as percent daily value. If you see the pearl millet can able to give you more than 50% of the daily methionine content. So similarly, so if you see the lysine content, it is less in the lysine content, where it could be able to give you only 20 to 25% of the daily value of the lysine content. This particular paper also we are coming. Let us first share the video of the same so that you can in detail you can see how the in vitro protein digestibility can be experienced. Ranjan sir, can you able to upload the video?
Yeah, just 1 minute. Please give me.
digestibility protocol. So for that, we have taken the sticky powder in the oil, 200 milligram of the flour. We will transfer in the oil, and we have to boil it for 20 minutes with 2 ml of distilled water. This is the boiling water bath. You can see the water is boiling. In this, we have to keep our flour, which is 200 milligram chickpea flour, in this oil, and we will keep it in the boiling water bath for 20 minutes by adding 2 ml of water so that the flour will be cooked. He is adding 2 ml of water. Now we'll keep it in boiling water bath for 20 minutes. In between shaking. After 20 minutes, we will take out our sample from the boiling water bath and we will transfer our whole content into the chemical flask. Whole content should be transferred completely into the chemical flask. Now we will add 35 ml of 0.1 normal HCl into it for to get the acidic pH into the content. 35 ml of 0.1 normal HCl. This is 0.1 normal HCl. This is the boil content into the flask. We'll add little amount of the water to the boil tube so that whole content is transferred into the conical flask. You have to mix it properly. We will keep it in shaker at 200 rpm at 37 degrees Celsius for 16 hours. Now we are keeping our content after adding 0.1 normal HCl into the incubator shaker for 16 hours, or you can say overnight, for complete digestion. 37 degrees, it will reach to 37, we are set at 37 and 200 rpm. So that whole content will be shaken and HCl will be mixed with the flour completely. After 16 hours of completed, we have to set the pH of our content to pH 2 as we are going to add the enzyme hepsin, because hepsin acts at the pH of 2, so we have to adjust the pH of our content to 2, and that will be adjusted with one normal alveolar. This is the content after 16 hours in a beaker. We are transferring from the flask to the beaker. This is the pH beaker, and this is one normal alveolar. 2 normal alveolar, sorry. With this, we will adjust our pH to 2 for the activity of pepsin. Now it is 0.88 pH. You can see it. With the magnetic stirrer, we have to adjust. Slowly we have to add our two normal NaOH, otherwise the pH can increase abruptly. Slowly drop by stop you have to add with a continuous stirring so that the NaOH will keep on mixing in our content. Now it is 1.23. Now slowly and slowly we will keep on adding. pH is highly important, otherwise our enzyme will not act. So we have to take care of pH. It is highly sensitive. Enzymes are highly sensitive to the pH and temperature. So we have to take care of this at the most. No, it is okay. It's up to 1.95. It's 2. It is okay. Now we'll stop adding to normal NaOH. Now our next step will be clean the pH meter. Our next step we have to add toxin in the content because in our stomach we have activity of toxin enzyme in acidic condition. So first we have make our solution acidic, the normality of normal, and we will transfer again our whole content into the flask. This is our toxin enzyme from Persian or from Sigma. You can purchase it, and you have to keep it at minus 20 degree always, otherwise the enzyme will not work. So you can see this is toxin enzyme. From this we have to take 3 milligram. We have to dissolve in 1 ml of 0.06 normal HCl of pH2. We have already dissolved and kept it. In his hand. Toxin enzyme solution, and we have 1 ml of containing 3 milligram of toxin. So we will add the 1 ml of toxin enzyme solution prepared in 0.06 normal of HCl pH2 in our content. And we will keep it for 3 hours. Again in shaking, mix the content properly, and we will again keep it at 37 degree for 3 hours at 200 rpm for the enzyme activity, complete enzyme activity. Filter, we will keep it in our content and toxin enzyme solution. 37 degree is set. We will shake it at 200 rpm for 3 hours. After adding toxin enzyme, the next step is adding the trypsin and chymotrypsin enzyme. And you know very well that trypsin chymotrypsin enzyme works at the pH of 7.4 in the body. So again, we have to adjust the pH of our content after toxin digestion to 7.4. 7.4, we have to know if it is normal 2 pH. Now we are going to adjust the pH. 0.4. For the activity of the enzyme, so in adjusting the period, I will show you the enzyme from Patria purchase from sigma. This is trypsin from porcine pancreas, and this is chymotrypsin from bovine pancreas. So you have to take the enzyme from very good company so that the activity will be optimum. Otherwise, the enzyme will not act if you take from local company. So from each of the bottles, we have to take 2.5 mg, 2.5 mg, and we have to dissolve it in 1 ml of 0.1 normal HCl, 0.001 normal HCl, and we have to add 1 ml of the enzyme mixture into the content after adjusting the pH. This is the purpose of pH 7.4. I'm repeating that pH is very important. So maintain the pH very carefully. pH is 7.4. Now 7.3 to 7.4 is okay. This pH is okay. 7.2 to 7.3. After the whole thing, the flask, the same flask, don't think of flask. And we will add our enzyme. Whole content. The system which is going in our body. So we are repeating the same system in our class. The taxing activity we have done. Now we are adding the trypsin and chymotrypsin enzyme for the complete digestion of the food material that are present in the chickpea flow. This is the enzyme solution which I have already discussed. 2.5 mg of trypsin and 2.5 mg of chymotrypsin in 1 ml of 0.001 normal HCl. Mix it properly and add into the content. Okay, we have to keep it for cooking for 5 hours after room temperature, that is 70 degrees Celsius and 200 RPM. So now we are getting the class in the refrigerator. Temperature is 47 and again RPM will be 200. The enzyme and the content will mix properly and our whole content will be digested with the extreme activity. For 5 hours, we have to keep it in the shaker. 5 hours, the thermoreduction testing digestion is over. Now we have to stop the reaction of our enzyme. So it will be done by using boiling water bath. We'll transfer our content in a salt tube and we'll keep the entire content in boiling water bath for 10 minutes. So all the enzyme activity, resting, thermoreduction system, everything will be stopped. Resting activity, even it has been stopped when we have added this buffer of 7.4 pH, 1 molar, 1 molar molarity. So by that addition of that buffer only, the enzyme activity is stopped. And if the system thermoreduction activity has been started. Now we have to stop the activity of that enzyme also. So we have to keep the entire content in the boiling water bath for 10 minutes. After 10 minutes, we have to cool the content and set the pH to 5.5 with sodium acetate buffer of pH 5.5, 50 millimolar for the mean hydrogen assay because mean hydrogen activity is optimal at a pH of 5.5. After cooling the entire content, we have to set the pH to 5.5 for the mean hydrogen assay. Mean hydrogen will detect all the primary amino acids which are formed after the complete digestion of the protein present in our tissue. So mean hydrogen assay will be the colorimetric assay that we will do after stopping the enzymatic reaction. After you can see that boiling step is over, we have cooled the content and we have transferred the content in the picture to set the pH for mean hydrogen assay, which is very much required. So with the sodium acetate buffer of pH 5.5, we will set the pH. This sodium acetate is 50 millimolar, 5.5 pH.
Just 1 minute.
is completed. Now we have to start with the menhaden acid. Like I have already told that menhaden acid will detect the primary amines present in the sample, which are digested by the actinopepsin and kinase. So, what we have to do for this, we have to prepare the menhaden solution. This is 3%. So 3% menhaden solution we have prepared in absolute ethanol, and it has to be very freshly, and it has to be covered with aluminum foil or in dark color bottles. Freshly prepare always. And for the sample tube, we need 0.33 ml of sample, extra sample, 1.66 ml of menhaden 3%, and reagent alcohol 0.5 ml. Total 1 ml of volume we have to make in append of tube. Similarly, one blank we have to keep. One blank which is only containing sodium acetate pH 5.5. 1 ml of the sodium acetate buffer. This will be blank with which we will set the our absorbance at 0. After that, we will take the reading at 570 nanometer of our sample, digested sample for the menhaden reaction. After that, calculation will be done. So he is preparing the sample tube. He is adding first. He has added 0.333 ml of sample digested, 0.166 ml of menhaden solution, 3%. And reagent alcohol also. Oh, reagent alcohol we have to put after keeping at 80 degree for 5 to 10 minutes. Try that. Blank and sample tube. 80 degree for 5 minutes. Yes, 5 minutes. You can see the menhaden solution that is has developed a blue color, which signifies the presence of primary amines present in our sample.
Yes, please come. Hmm?
5 minutes. Take out our sample and the blank tube. We can see that there is no color developed in the blank tube, and a blue color, very good blue color has been developed in the sample tube, which signifies the presence of primary amines present in our sample. Now we have to take the reading of both the tubes at the 570 nanometer in colorimeter. We will set at the 0 OD with our blank, and we will take the reading of our sample at 570 nanometer, and after that we will do the calculation part. Before taking the reading, we have to add 0.5 ml of reagent alcohol, 50%. This is reagent alcohol. 50% of reagent alcohol we have to add in both the tubes to make it up to 1 ml. Now we will take the OD for chickpea digested sample, which contains the primary amine after the action of pepsin, samothripsin, and peptide. Along with this, we have to prepare one standard graph also, which is L-glycine graph, L-glycine amino acid, which contains
the concentration ranging from 0 to 1 millimolar, and we have to make the volume up to 10 ml with the sodium acetate pH 5.5 water. 0 to 1 millimolar range we have to take for the standard graph, and after that we have to take the reading similarly, like we are taking for the sample at 570 nanometer, and we will prepare a standard graph. From the standard graph we will get the equation. From that equation we will calculate the primary amine concentration and protein digestibility depending upon the various formulas that we will discuss in detail afterwards.
So I think Dr. Vinutha, are you there?
Yes, sir.
Yeah, so I think I have played all the videos which was shared with me. So anything else to add upon?
If in doubt, if the trainings are having, then I can ask the question. Feel
So
free to ask.
okay, so I think all panelists will agree that she had nicely captured different steps in protein digestibility, especially the PDCAS, and then how to go for viability assay, especially in pearl millet powder. So now if you have any queries, any questions, please interact. So this is the chance where you can interact, or you can send your queries on chat box or on my mail, and she will answer. Any sort of discussion, model, anything, any suggestion, so that you can share, and Dr. Vinutha, she will answer. So I think so now we are at the fag end of today's schedule program. So that was two practical and then one invitee talk. So we have completed all these three. So tomorrow we are going to have a complete 3 hours with Division of Agriculture Engineering, where they are going to give you glimpses of Agriculture Engineering Division, the type of work which they are doing over there, the instrument which they have developed, especially for processing the grains of pearl millet. So some of the novel instruments they have developed recently, which is in demand. So they are going to show all those instruments, and then we are going to have a talk by one of the very experienced principal scientist, Dr. Pramod Kumar Sahu sir. He is principal scientist at Division of Agriculture Engineering. So he is going to give a talk on fabrication of instrument for pearl millet processing. So I think it will be very interesting for all of us. So now from land to lab, now we are moving slowly towards the plate. So processing is one of the part. So we'll devote one day for this, and then we'll go for the product and technology, which we have developed here. So one by one, we'll take up all those things. With this brief note, now I think I should thank each one of you. And before thanking, once again, wish you a happy Women's Day. So thank you for joining and being with us from last maybe three and a half hours. So thank you. Thanks a lot. Again, we'll meet tomorrow at 10 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you, sir.
Thank you.